Today we want to look at multiple zeros, but in order to do that we need to know how to differentiate, and we haven't had a chance to do that in our advanced class yet, so we need to do a little crash course here on how to differentiate. This will all be explained in far more detail when we do it in advanced, but for now we need you to be able to do it quickly. So I'm going to give you the formula. To differentiate something, if I give you a function where k is a number at the front and x to some power of n. To differentiate, what you do is that power of n, it comes down the front and it multiplies with the k. So you have n times k. X is still there, but you subtract 1 from the power, so that it becomes n minus 1. And the notation for differentiating is that you put a little dash there. So f of x was my original function. The derivative is f dash x. So it's a lot easier to see it in some questions. So let's have a look at example number 1 here. To differentiate that, I'm going to write f dash x equals, the 5 at the front is going to multiply, the 5 at the power is going to multiply with the 4 at the front. 5 times 4 is 20. The x stays there, but I subtract 1 from the power, so it becomes x to the power of 4. For question number 2, that's it, by the way. For question 1, that's finished. For question 2, to find the derivative, f dash x equals, the power is a 1, so 1 times by 8 is still 8, and it would become x to the power of 0 because you subtract 1 from the power. But x to the power of 0 is just 1, so the answer is really just 8. So any x term, the x will disappear and it will just be the number that's in front of the x. Question 3, to differentiate, we want f dash x equals. So because there's 2 terms here, we do each one separately. Differentiating the 5x, because it's just an x, remember that would just become the 5 in front of it. Any constant term, when you differentiate, disappears. So the answer for that is just 5. Now, it's also important to note that differentiating is a process of finding the gradient. So the gradient of 5x minus 2, hopefully you identify that as being a straight line equation, and the gradient would be 5. So my differentiating worked. Question 4, to differentiate this one, we want f dash x equals. For the first term, we bring the 3 down the front, leave the x, and subtract 1 from the power means it becomes x squared. Now we go to the second term, it's a 3x, so the x will disappear and it will just be a 3. And the constant term on the end does nothing for the gradient, so it is gone altogether. Question 5, we want to find the first 3 derivatives of this function. So the first derivative, we do f dash x equals. We take the first term, we bring the 4 down and times it with the 2. 4 times 2 is 8. X, subtract 1 from the power makes 3. Now we do the second term, bring the power down. 3 times negative 3 is negative 9. X, subtract 1 from the power, becomes squared. Then the last one, bring the 2 down, times it with the 4, makes 8x, and it would be to a power of 1. That's what we call the first derivative. To do the second derivative means we want to repeat that process. We put a double dash there, meaning second derivative, but the process is the same. We times the 3 with the 8 to get 24x, subtract 1 from the power is squared. 2 times by negative 9 is negative 18x, subtract 1 from the power, so just x to the power of 1. And the 8x, because there's just an x to the power of 1 there, would just become an 8. We want the third derivative, so that means we want 3 dashes, and we do the process again. 2 times 24 is 48x to the power of 1 because we subtract 1 from the power. The minus 18x would become minus 18, the x disappears, and differentiating the 8 is gone altogether. Okay, one more to practice to differentiate this one, the first three derivatives again. F dash x equals 5 times 7 is 35. X, subtract 1 from the power, is 4. Second term, 3 times 9 is 27. X, subtract 1 from the power, is 2. The minus x, that would be a minus 1 there. The x will disappear, so minus 1. And the 5 is completely gone. Second derivative, f double dash of x. 4 times 35 is 140. X, subtract 1 from the power, cubed. 2 times 27 is 54. X to the power of 1, and the minus 1 on the end will disappear. And third derivative, 3 times 140 is 420. X, subtract 1 from the power, squared. The 54x, the x will disappear, and it will just be a plus 54. Hopefully that makes sense. That's a very, very brief, quick lesson on differentiating, but we need that to do our lesson here. So here is what we're doing today. Your lesson is on multiple zeros for exercise 10G. A polynomial of degree n has n zeros. Okay, so a quadratic, so degree 2 polynomial, we expect 2 zeros. A cubic, we expect 3 zeros. But they are not necessarily all different, because sometimes we have doubles or triples, don't we? You say that alpha is a zero of multiplicity something greater than 0 when the factor occurs m times. So what that means is, if I look at these example here, if p of x equals x minus 1 cubed, x minus 5 squared, and x minus 6, then 1 from that first bracket is a multiplicity of 3. Before we would call it a triple, but now we want to talk about multiplicity. That's called a multiplicity of 3. The 5, because it has a squared there, we call that a multiplicity of 2. And the 6 is a multiplicity of 1. So quickly we want to practice that in example number 1 here. Find the multiplicity of the x equals 2 in each one of these. So the x equals 2 is this bracket here. So for the first one, it's going to have a multiplicity of 3. Which is what we used to call a triple root. For part B, we're looking for the x equals 2, which means x minus 2 when it's in bracket, not plus 2. So that has just a power of 1 there, so that would be a multiplicity of 1. And for part C, there's my x minus 2. It has a little squared on it, so it's going to be a multiplicity of 2. The multiplicity of a root can also be called the order of the root, and the root can be called a repeated root. Multiple roots are represented by stationary points or turning points or horizontal points of inflection on the x-axis. So we've already witnessed that when we were drawing our graphs. We knew that if we had even powers, then they were turning points, which means they came down and bumped off the x-axis. Or if they were odd powers, then they were points of inflection as they went through. So using differentiation, it is possible to factorize polynomials in order to determine their multiplicity, but there can be many steps involved in doing this. To shorten this work, we can find a first and a second, sometimes a third as well, and then find their zeros. So if x equals a is a root, we want to test the derivative. So if x equals a is a root, we want to test the derivative of our polynomial and substitute the a in. If that is equal to 0, then that means that x equals a was a double root. If we want to test for a double root, we would sub into the second derivative, and if that is still equal to 0, then that means it's a triple root. So every time you differentiate and it still equals 0 when you sub in, that means that it is an extra power on that bracket. This process can continue indefinitely, though we will usually only be dealing with single, double, and triple roots. So example 2 says to prove that p of x equals x to the power of 5 minus 8x to the power of 4, very long polynomial there, has a triple root at x equals 2. So first of all, we're going to do this process gradually. Normally, if we want to test if something was a root, we would just go, all right, let's sub in p of 2 into that polynomial. So 2 to the power of 5 minus 8, 2 to the power of 4, plus 25, 2 to the power of 3, minus 38, 2 squared, plus 28 times 2, minus 8. And we would type all of that into our calculator, and it does equal 0. And that told us, when we did our factor theorem, that that meant that x minus 2 was a factor of that polynomial. Now, instead of having to go to long division, which would be way too difficult for a degree 5 polynomial, we want to test to see if it has a higher multiplicity. So we start by differentiating. So the first derivative of my polynomial, this polynomial here, we take that first term, we bring the power down to the front. So 5x, subtract 1 from the power is 4. Then we do the next term, we do 4 times negative 8, so that's minus 32, x to the power of 3. Do the next term, 3 times 25 is 75x squared. Then we do 38 times 2 is minus 76x to the power of 1. And the next term, 28x, would just become 28. The x would disappear, and the negative 8 on the end would also disappear. So I've differentiated it. And now to see if I have a multiplicity of 2, I sub in p of 2 into that derivative. So that's going to be 5 times 2 to the power of 4, minus 32, 2 to the power of 3, plus 75, 2 to the power of 2, minus 76 times 2, plus 28. And guess what? That equals 0 again. So we know that this is at least a degree 2 on this factor here, but it might still be higher. We go to our second derivative. So working from this line here, the 5x to the power of 4 line, I go 4 times 5 is 20x, subtract 1 from the power is 3. 3 times 32 is minus 96x, subtract 1 from the power squared. 2 times 75 is 150, subtract 1 from the power, x. And the minus 76x will just be minus 76, and the 28 on the end will disappear. To see if my multiplicity is going to continue to increase, I sub 2 into that. Okay, and again, that does equal 0. So because I have got, so this means here that's a degree 1, so that's 1 multiplicity. This means a degree 2 for the second one. This is now a degree 3. So that I have proven that there is a triple root there already. So I can kind of stop there. I can go therefore triple at x equals 2. To be certain that it wasn't a degree of 4 though, we could differentiate it another time and see what happens when we sub 2 in. But we won't do that because we're running out of space. Let's go to question 3. My polynomial has a double root. Find the double root. So I haven't been given any root to start with, so I would look for possible factors. The possible factors come from that 4 there. The things that I can divide 4 by would be plus or minus 1, plus or minus 2, or plus or minus 4. Now I want to find a factor out of that, so let's start with p of 1, and guess what? That does equal 0. So that means that x minus 1 is a factor. Is it the double factor though? So we would differentiate our polynomial. P dash x equals 4 comes down the front, so it'd be 4x to the power of 3. 3 times minus 4 makes minus 12x, subtract 1 from the power, squared. 2 times 3 is 6x, subtract 1 from the power is 1, and 4x will just become a 4. The minus 4 on the end will disappear. Now, if the 1 is my double root, then it should equal 0 when I sub 1 into that derivative. 4 times 1 cubed minus 12 times 1 squared plus 6 times 1 plus 4. That equals 2, which means that x is equal to 1 is a single root. So I found a root, but it was only a single. I'm looking for a double. So I would go to my next possibility. What about p of minus 1? If I sub that in, yes, I get 0. If I sub it into my derivative, it does not equal 0 again, which means that it is a single root as well. If I sub in p of 2, it is also a root, it equals 0. When I sub it into the first derivative, I get 0 as well. So finally, that means that x equals 2 is a double root. Finally found it. Question 4. If p of x equals x to the power of 4 minus 4x cubed plus 6x squared minus 4x plus 1, then show that x equals 1 is a 0 of multiplicity 4. So we start to show, we want to show each multiplicity as we go. So we start p of 1. If I sub 1 into that, then I do get 0. I differentiate it, which is going to give me 4x cubed minus 12x squared plus 12x minus 4. And then I sub 1 into that derivative, which again gives me 0. I go to my second derivative. 3 times 4 is 12x squared minus 24x plus 12. And I sub my 1 into the second derivative, and it equals 0 again. I go to my third derivative of my polynomial. 2 times 12 is 24x minus 24, and I sub p of 1 into that derivative. So it's 24 times 1 minus 24, which, guess what, equals 0 again. I can even go to the fourth derivative using Roman numerals now. The derivative of 24x minus 24 is 24. When I try to substitute 1 in for the x, there is no x, so it's still just equal to 24, which means that that is not equal to 0. So when I'm checking my multiplicity, there's 1, 2, 3, 4. So I got to the third derivative equal to 0, which means it is a multiplicity of 4. Therefore, x equals 1 is a 0 of multiplicity 4. So to fully factorize that polynomial, it was a degree 4 polynomial. So you can see up here, degree 4 polynomial, and all 4, because it had a multiplicity of 4, all 4 of those zeros are at x equals 1. So the polynomial must be p of x equals x minus 1 to the power of 4. Question 5. If p of x equals 3x to the 4 minus 8x cubed plus 6x squared minus 24x plus 40. Then show that P of x has a 0 of multiplicity 2. So I need to go looking for my factors. So I've got a 40 here on the end. So there's quite a few possibilities here. P of 1 unfortunately does not work. It equals 17. P of 2 though does work. We get 0. So that means that x minus 2 is a factor. So rather than trying to hunt around for more factors, let's see if that has a higher multiplicity. So we want to differentiate. P dash x equals, differentiating 4 times 3 is 12x cubed. 3 times minus 8 is minus 24x, subtract 1 from the power. 2 times 6 is 12x and minus 24. So then I want to sub into that derivative 2. And when you sub in 2 into that derivative, you do get 0. To check that it doesn't have a higher degree than that, I need to go to the second derivative. 12 times 3 is 36x squared. 2 times 24 is minus 48x and plus 12. When you sub 2 into the second derivative, you get 60. So we have power of 1, power of 2, or multiplicity of 2, but not a multiplicity of 3. So we can say, therefore, x minus 2 squared is a factor. To fully factorize the polynomial, it's a degree 4 polynomial. We've found 2 of them and there's still 2 left to find. You could go back and keep checking all the possible factors of 40, but let's do a long division. So x minus 2 squared is what we've got so far. When we expand that out, that would be x squared minus 4x plus 4. Doing the division, the polynomial was 3x to the 4 minus 8x cubed plus 6x squared minus 24x plus 40. And we're dividing that by x squared minus 4x plus 4. So 3x to the 4 divided by x squared makes 3x squared. Timesing that out is 3x to the 4. 3 times minus 4 is minus 12x cubed. 3 times 4 is plus 12x squared. First ones cancel out. Minus 8 minus minus 12, so plus 12, makes 4x cubed. 6 minus 12 is minus 6x squared. Bring the minus 24x down. Now 4x cubed divided by x squared is 4x. 4x times x squared is 4x cubed. 4x times minus 4x is minus 16x squared. 4 times 4 makes a plus 16x. First ones cancel. Minus 6 plus 16 makes 10x squared. Minus 24 minus 16 makes minus 40x, and bring the 40 down. 10x squared divided by x squared is plus 10. Timesing it back out, we get 10x squared. 10 times minus 4 is minus 40x, and 10 times plus 4 is plus 40. So that makes a remainder of 0, which is perfect. So that means that we have the polynomial p of x equals our x minus 2 squared times by 3x squared plus 4x plus 10. And we would like to factorize that quadratic there, but unfortunately, when you use your discriminant, b is 4, so we get 4 squared minus 4 times a, which is 3, times c, which is 10. We get negative 104, so that means that there is no solution. We cannot factorize that quadratic. So part C, to solve our polynomial, the only place that we're going to get a solution from is from this one here. We can't get one from that second bracket. So that means that x is equal to a positive 2 is the only solution. As the 3x squared plus 4x plus 10 does not have any real roots. Okay, we are almost to the end. We have a little bit more to go though. The full menu of factorizing techniques. We're trying to bring everything all together here. First of all, number 1, test whether some low positive and negative whole numbers are zeros. If all coefficients are integers, every integer 0 is a divisor of the constant term at the end. Question 2, test each 0 using our derivatives to find the multiplicity. Part 3, use the sum and product of zeros to find their zeros, so we might have to find some extra ones in there. And part 4, if all else fails, multiply the known linear factors together, use long division if the coefficients of p of x are all integers. Then any integer 0 p of x must be one of the divisors of the constant term. So question 6. The polynomial has a double 0. First of all, we want to find the double 0. So we've been going for quite a while here. I'm going to tell you straight away, we'll be checking for factors of 2. If I sub in p of minus 2, I am going to get a 0. So that means that x plus 2 is going to be a factor. Is it the one that has a multiplicity of 2 or a double 0? We would check that with our derivative. So 9 times 3 is 27x squared plus 24x minus 11 for the derivative. When we sub in minus 2 into that derivative, we get a positive 49. So that is not the double 0. Unfortunately, you cannot find the double 0 by subbing in any factor of 2. So we found one 0 though, and it's only a cubic polynomial. We could find the others. What we can do instead is we know that the derivative has to be equal to 0. So the derivative that I found, this 27x squared plus 24x minus 11, if I make that equal to 0 and work backwards to find out what x must have been, so 27x squared plus 24x minus 11, I want that to equal 0. So let's solve that. We want to times minus 11 with 27. So we have minus 11 times 27, which is minus 297. And we're looking for two numbers that times to give minus 297 and adds to give the 24. Now they're quite big numbers to work with, but it is a positive 33, so plus 33x, and a minus 9x. Then we need to factorize that in pairs. So the first two terms I can bring out a 9x, which gives 3x. Actually, I'm not going to do the first, so I'm going to do the first one and the third one. I can bring out a 9, because I can't bring 9 out of 33. 3x take away 1. Then doing the second and the fourth one together, I can bring out an 11, which gives me 3x take away 1. Then I can bring the 3x minus 1 out the front to be 9x plus 11 in the second bracket equals to 0. So from the first bracket, I get x is equal to a third. And from the second bracket, I get 9x equals minus 11, or x is equal to minus 11 over 9. Which one of those is my 0 that I'm after? Now, looking at my equation up here, knowing that there's a 9 there, and knowing this is a double, then having a 3 in my solution, 3 squared is going to make a 9. So it's most likely going to be this one here. But let's check. We would check by subbing them in. So let's p of 1/3, if I sub that into my polynomial, you do indeed get 0. If you sub p of 1/3 into the derivative, you also get 0. And therefore we've shown that there is a double 0 at x equals 1/3. Find the remaining zeros to fully factorize. Now, we have a double 0. We actually kind of already know this because we found one of them up the top. We do, but let's assume that we hadn't found it because I need to show you a little technique here. We know one of the solutions is going to be x plus 2. But if we didn't know that already, we could write this down as our polynomial is equal to 3x minus 1 squared. Now I've written that's my x equals to 1/3. I've written it in that form because I know I have a leading coefficient of 9, and that's going to give me a 9. I know that it's a cubic, and I know that there needs to be another factor here, so I'm going to call that x minus alpha. So then I'm going to substitute a point into that equation to work out what alpha is equal to. So looking at my basic equation up here from the start, if I subbed in x was equal to 0, I would get y is equal to 2. So that's an easy point to sub in. So sub x is 0 to find the 2. So that means 2 equals 3 times 0 minus 1 squared is equal to 0 minus alpha. Now 3 times 0 is 0, minus 1, and minus 1 squared is just 1. 0 minus alpha is minus alpha. So I get alpha is equal to a -2 when I divide that across the other side, which as we were kind of already expecting because we had been sneaky and found that previously. So p of x is equal to the 3x minus 1 squared times by x plus 2 for the third factor. Finally, we make it to our very last example. Example 7. The polynomial p of x equals ax cubed plus bx plus c has a multiple root at -1 and has a remainder of 8 when divided by x minus 1. If a, b, and c are real, find their values. So my polynomial is ax cubed plus bx plus c. I'm told that it has a multiple root at 1. So if I differentiate, instead of going hunting for it, let's differentiate, and that would be 3 comes down the front, so it'd be 3ax, subtract 1 from the power squared, plus the b. Now a multiple root at x equals -1 means that p, the derivative at -1, has to be equal to 0. So if I sub that into my derivative, the p dash x equals 0 and x is equal to -1, so it's 3a times -1 squared plus b. I get an equation, 3a, -1 squared is 1, plus b. So b is equal to -3a. Okay, that's my first bit of information. I'm going to call that equation 1. Also, we were told in the question that when the polynomial was divided by x minus 1, we get a remainder of 8. So that means if I sub in p of a -1, oh no, p of a +1, sorry, p of a +1, so I'm going to do the opposite of that in there, is equal to 8. Subbing that into my polynomial, the polynomial is 8 and the x is 1. So it's a times 1 cubed plus b times 1 plus c. So that is 8 equals 1 cubed is just 1, b times 1 is 1 plus c. So I have another equation, but unfortunately that one has 3 pronumerals in it. What else do we know? We know that it is a factor. We do know that x equals -1 was a factor. It was a multiple root. So we could use that piece of information again to say that p of -1 is equal to 0. And if I sub that into my polynomial, I would get 0 for the polynomial equals a times -1 cubed plus b times -1 plus c. So that's going to give me -1 cubed is -a, -b plus c. Now I am going to have to try to use that equation and equation 2. I'm going to have to try and eliminate some things here to try and find out what a, b, and c are. So this is going to be equation 3. So we have equation 1 there that is just in terms of a and b. So if I sub equation 1 into equation 2, let's start with that. Sub 1 into 2. That's going to be 8 equals a plus b, but instead of b we have -3a plus c. So a minus 3a is -2a plus c. Let's get the c by itself for that. So that will be 8 plus 2a. Okay, so that's going to be equation 4. We can also sub equation 1 and 4 into equation 3. Okay, so that's a bit tricky. We have equation 3, which was 0, equals a minus a, and then minus b, but instead of b, we're subbing in -3a, so that will become a plus 3a. And then it's plus c, but instead of c, we can sub in that c is equal to 8 plus 2a, which is our equation 4. By doing that, we have got an equation with just a in it. So -1 plus 3, so that's -2, plus 2, sorry, plus another 2 is 4. So we have 4a plus 8. Move the 8 across and divide by 4. We finally get one of our solutions. A is equal to -2. Then we want to find b, so we put that back into equation 1. So that's -3 times a, which is -2. So b is equal to 6. And finally, to find c, we put it into equation 4. So it'd be 8 plus 2 times a, which is -2. And that equals 4. So A equals -2, B equals 6, and C equals 4. Wow, what a question. And we're done with the topic.